One more thing to do as a warm-up is to talk about this interesting little corner of the standard library, include utility. So I'm going to talk about a type that's found inside of this header, although actually we're going to find ourselves using it all over the place later in the semester because it turns out to be quite useful, even though at first it seems sort of unnecessary. It seems sort of like just extra structure with no reason to use it. And it's a type that we can use to combine pieces of data together in a sort of convenient and lightweight way, a little bit lighter weight than making a structure. So suppose I want to send you a single data item that contains both an int and a string. So I want to send you one piece of data, for example, as the return value for a function. Well, of course, I could make a structure that contains an int and a string and send you that. But that might be a lot of work. I mean, making a structure just to return something from one function. And what if later I want to return an int and then a float, or an int and an int, or a string and a string, or a string and an int, or something like that? Well, making all those structures is a bit of a mess. It turns out the standard library contains, a variety of different features that can help us with this, but the one that we care about for today, because it's nice foreshadowing of something later, is this type called Std Pair. And we'll use the angle brackets. It turns out that Std Pair is a parameterized type, just like vector, except that it takes two type parameters. And it's a pair of two things. We would call it an ordered pair. That is to say, it contains a first thing and a second thing. And I would like to make a pair that contains an int followed by a string. And I'll call it p. And I can initialize it in a variety of different ways. I'm going to begin by initializing it directly with its initializer, and we'll see that it turns out when you use these later, you often don't write these initializers. There's actually a faster way of doing it. So this creates a single object called p that contains an int and a string. And then I can use it. So I could say first, I don't know what we call this, first element. Would be p dot first. And notice that it looks a lot like p is some kind of structure. So the dot operator, and it turns out it is sort of a glorified structure. It's got one interesting characteristic, which is the use of angle brackets with two different types. Other than that, it is in all ways that we care about for the time being, basically a structure. So dot first and dot second refer to the two elements of the pair. And of course, it's an ordered pair, so we care which one comes first and which one comes second. We can see there it is. I've got the value 5 and then the string hello world. A couple of notes though. So first, having to write out this long compound type, you could argue is not really any easier than making your own structure. But the standard library provides us a couple of clever tricks that make it pretty easy to make these things. And in particular, they make it easy to make these things without having to worry so much about what the types of everything are. So there's a function, a sort of magic looking function called makePair. And makePair takes two arguments, the first thing and the second thing, and they may be of any type. And then it returns, as its result, it returns a pair object of the type of the first thing and the type of the second thing. And actually, maybe to make that absolutely clear, I will start with this. Just to prove to you that the actual return value of makePair is what I'm saying it is. So makePair takes, in this case, an int and a string and returns an object of type pair of int and string. If I were to change it later to instead take, let's say, an int and an int, in this case, it's going to crash because, or the compiler will give an error because makePair is expecting that I should be taking a pair of int and int, but it's instead being stored in a pair of int and string. But if I change it to be a pair of int and int, and I try compiling it, then it works. And that's one reason why, of course, why would I bother writing this type out in full when I could just use auto? So it's one great use of the auto keyword. As we get to this point in the course and the types that we're working with become more and more complicated, auto is more and more useful to avoid having to write them out. So when you create pairs, often you call this standard library function makePair that seems to be able to take arguments of whatever type you throw at it. And it automatically creates you a pair of the correct type. Now, just like before, keep in mind, auto is not a type. So once this pair P has been created, it's a pair of int and string, which means from now until the end of P's lifetime, the first element of P is an int and the second element of P is a string. If I try and change them, I can change P.first to be some other int, but I can't change it to be a type other than int. So makePair is a little bit mysterious because it seems to be able to take whatever I throw at it and make a pair out of it. It turns out that actually the magic behind this is the same magic that works with angle brackets, like the ones with vectors and pairs. We're going to see later in the course how to make this work. It's interesting, but not nearly as magical as it seems once we get there. So the Std pair type is a convenient way of packaging up two values into one object without having to go make your own structure. Now, that said, you might look at this and say, but what's the point anyway? Like, this sounds like a new thing we have to learn, Bill, and you promised we wouldn't need to learn new concepts if old concepts did the trick. And in fact, last time I covered this in person, so during the in-person 2021 semester, when I actually talked about this at the beginning of a lecture, somebody did put their hand up and basically said that. They said, come on, this is the exact opposite of the way you do things. Why are you making us learn this weird little toy when we don't have to? And the answer is, if you watch a couple more videos, you'll see why. We actually need this type for something we're about to see that we do really need, that is a brand new thing that we can't do otherwise. But also, this does give me a good excuse to talk about whether you believe in this idea of this being more convenient than the structure or not. I want to talk about sort of the converse operation. Here I have two values and I'm packaging them together into a single pair object. But it turns out C++ supports unpacking objects as well. And so maybe what I'll do is I'll also demonstrate that I can write a function that takes a pair as an argument. So I'll call this function f. And so f is going to take as its argument a variable of type pair of int and string. And we'll call it the pair. Now, of course, if I wanted to, I could print out in f. And then I could just print out the pair dot first, and then a space, and then the pair dot second. And so we'll try that first. And sure enough, when I get inside the function f, it takes a pair containing an int and a string, and it prints out 5 and hello world. Okay, great. We knew we could do that. Of course, I can pass pairs into functions. We can also do this, though. We could say, I'll call them first and second. Now, I'll call them x and y. I don't want to use the same names to avoid confusion. We are allowed to also do this. This interesting notation, so auto and then a bunch of names in square brackets, is used to unpack an object with multiple members into its constituent parts, and it creates a variable for each of them. The type has to be auto because the types of the things I create could be different. So for example, if I unpack this thing called the pair, it's a pair of an int and a string. And so the first thing I unpack is the first element, the int, and then y is the string. And so when I use this unpacking notation, and I made a note to myself before the video, the actual name for it in C++ is, maybe I'll write it down, structured binding. I use the term unpacking for this. I believe that the manual for C++ does sort of acknowledge that unpacking is an okay term for it. I think the reason I use the term is from Python. So this notation is relatively new to C++. I think that it was C++ 17 that brought this in. Whereas Python has had this for a long time. So when I learned Python originally, which was around 2007 or 2008, Python already had this. And so back then I called it unpacking. That's why I'm going to call it that in C++ as well. So I'm allowed to take this variable and unpack it into individual other variables because it contains compound data. Now, for the time being, we haven't yet seen what happens if we create our own smart objects like vectors or strings. With the structures that we're creating, it turns out we can unpack those as well. Pairs are not special. Std pair is a glorified structure object. The reason we can unpack it is because it's a structure object, not because pairs are somehow different than other objects that we've seen. We'll verify that this works. And sure enough, it does. Okay, so what have we seen in this video? Well, so far we've seen there's this type called Std Pair, which is a convenient way of packaging together data, two pieces of data, into one object. For example, to return from a function or something, if you don't want to make your own structure for it. We've also seen that the make pair function can produce pairs very conveniently, and that the auto keyword avoids us having to know the tedious details of a type name. And finally, that once I've packed things together into a pair, I can unpack them with this interesting notation. Just to be clear, you have to use the word auto when you use the unpacking notation. You have no other choice because the things you unpack can each have different types. Let's talk more about unpacking. So in this file, I've got this type called date, which is 3 ints, year, month, and day. And I've got a function print date. This has been cannibalized from a previous example. I have a function called print date, which takes a date object by constant reference and prints it out. Here's a rare case of me forgetting to put use my new convention for where I put the word const. Okay, so it takes a date and then it prints it out. And here I have two date objects, and as the comment points out, we can view the use of this type date as a convenient way to pack together year, month, and day, to pack three integer values into one object. And so conversely, I suppose I might want to unpack them. And we see here the use of the unpacking notation. I take the date object D1 and I unpack it into year, month, and day. The order of the things I unpack is the same order that they are defined in the structure. So year comes first in the structure, and that's why year comes first when I unpack it. So I'll try compiling this. It's also true because, as we've seen with the auto keyword, by default, if I use auto to declare a variable, what I'm creating is a new legitimate variable of its own. And so that means that, I guess conceptually, I've got this object of type date here, and it's got a year and a month and a day. And they are set to 2021, 12, and 30. What I'm doing on line 34 is making three separate variables, y, m, and d. And that means that if I modify y, m, and d, I'm modifying a copy. I'm not modifying the original. I suppose I didn't really have to draw that all the way out, but you get the idea. So the unpacking that I'm doing on line 34 is making three new variables that are independent, that behave as their own variables. They all will end up having type int. The auto keyword the unpacking notation results in the variables that I extract having the same type as the members of the structure that I extracted them from. In the event that I want to make, I would like to use those variables as references into the original structure, I can write auto ampersand. And I can prove that here. So in this piece of code, I extract D1, I unpack it into Y, M, and D. And when I do that, I can then print them out. I then unpack D2 into three references. So these variables YR, MR, and DR are just new names for the members of D2. So if I modify them and then I print out D2, I am going to see a modification in what I've printed out. So if I change the day number in D2 to 17 using DR, I should expect that to be reflected when I print it out. And then finally down here, we just rehash what we just saw in the previous example, which is if I use make pair to construct a pair of, in this case, string followed by int, I can then unpack that pair using the same notation. So the key thing to observe is the unpacking notation is not unique to pairs. It is, in fact, defined for a variety of different data types. Exactly what you can apply it to is sort of complicated. There's a bunch of different stuff. But basically, anytime I have a data structure that consists of an unrestricted set of data items where the number of data items is fixed in advance. So a date object is 3 ints. It'll always be 3 ints during this program. And a pair object is obviously 2 things. As long as it's a data structure that has a fixed number of members where there are no access restrictions on members, and I can't be any more specific about what I mean by that, although we'll see pretty soon. As long as there are a fixed number of members and there's no restrictions on how they can be accessed, you can unpack them. That's the short version of that story. And so we'll see the unpacking notation is quite useful for when we package stuff up into structs to send them around the program, we often want to take them back out to then work with them. And so we can use unpacking notation for that. And we can also use Std Pair as a convenient way of packaging stuff up if we don't want to go through the trouble of making a new structure type.